Right, this is an arrangements question, really interesting but challenging. I'm going to talk about it, two different methods for going through it. First of all, this is essentially how I did it. I kind of considered the idea of arrangements when, let's say you have A, B, C, but we're just basically interested in putting A, B, C down in some arrangement. Now there would be three choices for the first letter, and then two for the second. And we would times these together to give all the different arrangements. Because for every A, there's two choices here, but you could put B first, and then there'd be two choices, and then C. So six in total. And then for the last one, you've only got one choice because it's whatever is left over. So it's six. So I can bring that idea into this question here. And I'm going to do that in the same kind of way. So there's actually nine choices for the first number. And I'm going to imagine that I don't know, I put in a 4. Um, Actually, I'm going to make it 3 for reasons that'll be a bit easier to explain in a minute. Right, now for the second one, actually, it might seem like I have 8 choices, but I need to be a bit careful because if I put a 6 in here, then I would have to put a 9 here to make the three adjacent boxes a multiple of 3, but then I wouldn't be able to put one here. So actually, I can't just put any number in that second box. It can't be a multiple of 3. Um, and the thing is, if I put a different one in, like a 1, then if I put 4 here, then to get a multiple of 3, um, I've got 5, I'd have to put 7. That's the only number that will be left, but then I wouldn't be able to get a multiple of 3 here. So in the second method, I'll talk a little bit about this, but we have to be careful. Basically, some of them kind of link together. So in fact, there are not 8 options for here because I'm not allowed to put in a 4 or 7 in this case. So actually, there would be 6 options. So let's say I put in a 3. Okay, there we go. Right, now I want to get a multiple of 3 from the 3 adjacent boxes. So I can either put in a 2 or I could put in a 5. So that will give me 9, or I could put in an 8. Those are the only options. And you can see there's a bit of a link going on. We seem to have 1, 4, and 7 linking together, 3, 6, and 9, and now 2, 5, and 8. Okay, but there's going to be 3 options overall. So let's say I put a 2 in. Okay, brilliant. But now I have to consider that I've got a 5, and I need to get a multiple um, of 3. So I can't put 1 in, but I could put 4 or 7 in up here. So actually, it's going to be 2 options now. So 4 or 7, that's the only one that will work. And now I'm at 6. So to keep it as a multiple of 3, I'm going to have to put in another multiple of 3. I can't put in 3. I could put in, say, 6, but there's going to be 2 options because I could put in 9 instead. Now I'm at 10. You can sort of see this continuing. So I can't put in 2 because I've already used it. I could put in 5 or 8 now. So there's going to be 2 options here. So let's say I put in 5. Okay, I'm on 11. 1 would work, but I've already used it. 4 would work. I'm going to have to put in 7. Actually, there's only one choice here. And now I'm at 12. I'm going to have to put the 9 in to keep it a multiple of 3. So one choice. And now I just need to put the final one in. One choice there. So I hope you're happy with this. I'm happy, like I've explained the 9 and some of these here. I think the hardest one to explain is this 6 to justify it. So I've tried to explain that I can't, yeah, basically if I put in 4 or 7, it would cause problems because if I put, I'm just going to say it again, if I put 4 here, I would have to put 7 here, but then there's nothing I can put here. So basically I rule 2 out, and that would be the case whatever my starting number was. If it was a 2, then I wouldn't be able to put a 5 in, because then I would have to put 8 in, and then I wouldn't be able to put 1 there, and so on. So the number of arrangements is as shown. It's not quite in the form written above yet, so you can see there's some 6's though. So let's just go with it. You can see that I've got 6 times 6, and then I could split the 9 into 3 times 3, and then I'm also timesing by 2 times 2. So actually I can put these together and these together, and it's in fact going to be 6 times 6 times 6 times 6. And our answer is A. Okay, that was my first effort of explaining how to do this problem. Um, it's quite a nice approach, just got to be careful and justify everything along the way. Right, method 2 from this problem. This is really taken from the answers, and I like it because it kind of explains where the 147 link comes from. So let's say now that our starting numbers are A, B, C, D, or any four adjacent, to be honest, to A, B, C, D. Now we know that these are multiple 3, A plus B plus C is a multiple of 3. But so is B plus C plus D. So that means if you subtract them, so let's say we've got A plus B plus C minus B plus C plus D is as well, because we're just going down the times table. And these cancel and these cancel. So A minus D must be a multiple of 3. So this leaves we could have different groups. This leaves different groups because the same is going to happen for exactly the same reason here. It must be that these are all basically 3 different from one another. And we're going to get 1, 4, and 7. And then these must be 3 different from each other. So we could have 3, 6, and 9. And finally, it could be these must be 3 different from each other. 1, no, not 1, I've already dealt with 1, 2, 5, and 8. Okay, so we now can think about the different ways of arranging these like little groups of numbers, essentially. So we could put 1, 4, and 7 here, for example. But there are 3 things that I'm arranging, so there's going to be 3 factorial ways of moving these around. Next up, we can decide which one goes here or here. So let's say we put 3 here, 6 here, and 9 here. Then there's going to be another 3 factorial ways of moving them around. And then finally, we've got 5, 8, and 2. And again, 3 factorial ways of arranging those. Now, the thing is, I don't have to have 1 on the left, and I could have put 5 ahead of the 3, for example. So if you think about a given box, for example, I can also arrange them in 3 factorial ways. I could have 1, 3, 5, or 5, 3, 1, and so on. There would be a knock-on effect, but it would still, be incorporated in these. So what I have to do right at the end is just times by 3 factorial to account for the fact that I can arrange, a single box in 3 factorial ways. Once I've done that, then within that, I could then arrange the others in 3 factorial times 3 factorial times 3 factorial ways. But overall, that is my argument, and that is going to be 6 times 6 times 6 times 6. So works, this argument was very different, but we get the same answer. So I hope that gives even further insight to this problem. Nicely done and well done on this problem and this challenge, and thanks for watching.